Welcome to the lesson on graphical analysis. Upon completion of this lesson, learners will be able to discuss statistical process control, construct X-bar and R charts of a sample of data, and assess X-bar and R charts to determine if a process is in control. Companies use quality control to ensure that their products are the right weight and size and perform consistently well. In a manufacturing setting, quality control and consistency is important. So how do you know if your processes are in control? Data collection and analysis can tell you how your company processes have behaved over time. Graphically representing data, like in a histogram, provides a great picture of what a data sample looks like. You can also collect and graph data on how a process has behaved over time. The process of using statistical methods to control quality is referred to as statistical process control, abbreviated as SPC. SPC aims to reduce variability in a system by recognizing it early on and determining the cause of the variability within the system being observed. The goal of SPC is to reduce variability in processes. There are two types of variation in a process: common and assignable. A common variation is attributed to normal or chance sources of variation that exist in the process. An assignable variation is attributed to a specific cause that results in a loss of quality control. An experienced manufacturing operator is able to detect and identify the most assignable causes of variation due to their years on the job. However, this is a skill that can be easily acquired with the right training. Control charts are essentially trending charts that contain a center line and upper and lower control limits. The control limits help you determine when the variation in the product moves beyond quality control standards. Control charts are usually on a time or sequence scale. This means that samples are taken at distinct time intervals, say every hour, or they are taken in a specific sequence. There are two control charts used together to determine quality control: the X-bar chart and the R chart. The X-bar chart looks at the average of each of the samples and plots them on a graph. The R chart tracks the range of the sample over time. Let us look at a relevant example. A battery manufacturing company manufactures lithium-ion battery packs for electric vehicles. These battery packs provide energy storage and power delivery for various EV models across the automotive industry. The company produces three capacity variants: 20 kilowatt-hour, 50 kilowatt-hour, and 100 kilowatt-hour. The Quality Assurance Department has been receiving complaints that the 100 kilowatt-hour packs show inconsistent capacity readings. Additionally, the charging infrastructure team has reported higher than normal stress on charging equipment due to packs drawing excess current. The Quality Assurance Department suspects that their cell testing and pack validation system needs calibration or replacement. To provide evidence for this upgrade, they decided to collect sample data on the capacity of 5 battery packs per day over a period of 20 days. The data they collected is shown in the table on this slide. In the next few slides, we will walk through the steps needed to construct X-bar and R charts for this data. We will now go through the various steps to construct an X-bar chart for this scenario. Step 1. Calculate the mean and range, R, of each sample. Utilize the information from the previous section to calculate these values. Use the table on the slide to check your work. Step 2. Calculate the center line for the chart. The center line for the chart is the mean of the entire sample data. It can be found by adding all the means of each sample and then dividing by the number of samples. The calculation of the overall mean, X-bar, for the sample data in the table is shown below. In step 3, the average of the ranges is calculated as the sum of the ranges of each sample divided by the number of samples. Therefore, the center line of the R chart and the average of ranges is 3.6. Step 4. Determine the upper and lower control limits for the X-bar chart. The upper limit on the chart is established at approximately 3 standard deviations above the center line. Similarly, the lower limit on the chart is established at approximately 3 standard deviations below the center line. Since we do not know the standard deviation of the population because of the small data sample, an approximation must be used instead. The approximation is a factor of the average of the ranges, and A2 is a factor based on sample size, which, from the table we see, is 0.577. The formulas for the upper and lower control limits are seen here. From our previous calculations, we know that the X-bar equals 102.1 and that the R-bar equals 3.6. Therefore, our upper control limit for the chart is 104.18 and the lower control limit for the chart is 99.91. Note that the upper and lower control limits and the center line might be determined by the quality control department and not by the frontline production technician. However, it is important for frontline production technicians to understand where these control limits come from and why they are important. Step 5. Construct the X-bar chart. Collecting the data and plotting the sample means is on the chart and is the responsibility of a frontline technician. The x-axis represents the number of the sample collected. It could also be represented by the time that the sample was collected. The y-axis represents the average of the sample. In this case, the average is in terms of kg. Next, the center line and the upper and lower control limits need to be graphed. Now, the mean of each sample calculated in step 1 is to be plotted on the graph with the upper and lower control limits and center line. The X-bar chart is constructed and presented here. Now, let us construct the R chart for this data. Step 1, calculate the center line for the R chart. The center line for the R chart is the average of the ranges. The average of the ranges was calculated in step 3 of the X-bar chart, and it is equal to 3.6. Step 2, determine the upper and lower control limits for the R chart. The formulas for the upper and lower control limits are seen here. From our previous calculations, we know that R bar equals 3.6. From the table on the slide, we can determine that D4 equals 2.115, and D3 equals 0. Therefore, our upper control limit for the chart is 7.51, and the lower control limit for the chart is 0. D3 and D4 are control chart constants that depend on the subgroup size. They are used to calculate control limits and estimate the process standard deviation. Step 5. Construct the R chart. Collecting the data and plotting the sample means is on the chart and is the responsibility of a frontline technician. The x-axis represents the number of the sample collected. It could also be represented by the time that the sample was collected. The y-axis represents the average of the sample. In this case, the average is in terms of kg. Next, the center line and the upper and lower control limits need to be graphed. Now, the mean of each sample calculated in step 1 is to be plotted on the graph with the upper and lower control limits and center line. So now that you have your X-bar and R chart completed, what do they mean? What information can you get from these charts? A process is considered to be under control when all the means and ranges fall within the determined control limits. To determine if a process is out of control, there are a few conditions to look for in your charts. If any one of these conditions is present, then the process is out of control, and a root cause investigation should be done to determine the cause of such process variability. The first condition to look for is when one or more points on the chart are above the upper control limit or below the lower control limit on either chart. This means that the particular sample had large variability, and the processes did not stay within the company's desired specifications. The second condition is a trend pattern. If you see 6 or more consecutive points on the chart that trend in the same direction, either up or down, then the process is out of control. The third condition is called a jump shift pattern. This occurs when 9 or more consecutive points are on one side of the center line. If there are 9 points in a row above the center line, or 9 points in a row below the center line, then the process is out of control. The fourth condition is called a repeating cycle. This is any visible cycle that you can see in the data where it consistently follows the same patterns. This means that there are external factors dramatically affecting the data in a cyclical manner, and the process is not in control. The fifth condition is called a cluster pattern. This occurs when there are groups of points clustered together in the 3 zones of the charts. Each zone, A, B, and C, corresponds with the standard deviation away from the center line, with zone C being the closest to the center. When 2 or 3 points are in zone A or beyond, then the process is out of control. Also, if 4 or 5 consecutive points are clustered in zone B or beyond, then the process is out of control. The sixth condition is called a mixture pattern. This occurs when the points alternate jumping across the center line. Also, no points are near the middle of the chart in this condition. This shows that there is very little consistency within the process being analyzed. Lastly, the seventh condition is called the stratification pattern. This occurs when 15 or more consecutive points are in zone C of a chart. Using the conditions previously described, let's look at the X-bar chart we constructed earlier. Is this process in control? No. The process seems to be out of control because the mean for sample 10 falls below the lower control limit. In the same way, let's revisit the R chart constructed earlier. Is this chart in control? Yes, this chart appears to be in control. The R chart does not exhibit any of the trends described in the conditions. In general, if you find that an R chart is out of control, then the X-bar chart is not valid. To aid in communication, it is best to circle any rule violations on the charts and then investigate the causes of the out-of-control situations. If you were the frontline technician who analyzed these charts, your next step would be to inform the quality control department about the data point that is outside of the control limits and assist in determining the root cause. In summary, constructing and analyzing X-bar and R charts aids in determining if a process is out of control and can help pinpoint the root cause of the problem. These tools can be used to improve the overall quality of your processes and, in turn, your company. Thank you.